Welcome back. This recording, the very last in the filters material, filters chapter, will look at problems primarily on the band pass and band stop filters. And I also have just a couple of simple examples from the active filters chapter also, just to, not that I expect you to prepare for an exam question on active filters, but I thought I'd still do an example or two just to make sure that you understood some of the basic ideas on active filters also. So mostly what we are going to do in this session is to look at the examples and some problems for band pass, band stop, and some active filters. Okay, so I am on slide 23 of the PPT, and one second while I get organized. Yeah, okay. On slide 23, and this actually is a resonance problem example that I had already covered last time. So we don't really need to go through this in any detail. All I wanted to point out is that these same equations that you see here on the slide to solve for um, the resonant frequency, the corner frequencies, the bandwidth of this problem, the same kind of formulas are what we will use for the remainder of the exercise today. Okay, so let me skip to slide 29. Okay, that's where we have our very first examples from the textbook for band pass filters. So there's actually three examples: 14.5, 14.6, and 14.7. And I've grouped together 14.5 and 14.7 because they are both about the series circuit, series RLC implementation of a band pass filter, while 14.6 is a parallel circuit implementation. So let's look at 14.5 and 14.7 first. 14.7, the only additional thing that happens to the circuit is that there is now a series resistance, a source resistance Ri in series with the rest of the elements, and so that has been shown separately, so we'll take a look at that. Okay, so 14.5 then, and I'm slide 29 again, is a series RLC implementation of a band pass filter for a bandwidth of 1 kilohertz to 10 kilohertz. The example is written in a nice way. It's on page 555 of the textbook, so if you have some time, take a look. Again, if you're interested in music, electronics, audio electronics, you might enjoy reading this example because it talks about the audio frequency band 0 to 20 kilohertz. Within that, we are trying to design what's called a graphic equalizer. You may know what these are. These are sliders or rotary buttons on amplifiers that help you boost just one set of frequencies. So here this is for a 1 kilohertz to 10 kilohertz boost. So the challenge for us is to design a suitable RLC filter that can give us amplification of only this band. So anything below should be cut off and anything above should be cut off. So we need just 1 to 10. Okay. So there are a number of approaches that the textbook says we can take, and I will let you read it. But he finally ends up choosing one method, and let's just quickly look to see what he does. So he begins by choosing a 1 microfarad capacitor in the circuit. Now, we are also given the 1 kilohertz to 10 kilohertz. So, with these two things, this one assumption and one given value, we should be able to compute everything else. Okay, so let's see how he does that. So he uses the geometric mean formula, and notice that he is actually directly working in hertz. He doesn't convert that to omega radians. I think that applies in all the formulas we have studied for filters. Sometimes you absolutely have to use the omegas, particularly when you're trying to you find, let's say, L or R um, using the definition of the center frequency or the definition of bandwidth beta. You must, I think, talk only in terms of omega, but a few other places you can use F also directly. So be careful which applies, which doesn't apply. And so if you do some problems, you'll know where to be cautious about that. So anyway, he directly applies a formula for the geometric mean to come up with the center frequency F0 as 3162 hertz, and this is the geometric mean of the band that we have been given. The band is 1 kilohertz to 10 kilohertz, right? So if you do that, if you take the geometric mean of 1 kilohertz to 1 kilohertz and 10 kilohertz, you come up with 3162. Now, using this value in the formula for omega 0, the center frequency, which connects L and C, and we already know C, we have assumed 1 micro, he comes up with a value for L. The only caution again is, remember, when you're using this formula, you have to convert to radians. So he takes the center frequency that he derived in hertz, first converts it to radians, and then applies the formula, and he comes up with a value for L, which is 2.5 millihenries. Then the bandwidth, he still figures out as 9 kilohertz. He keeps that uh, in kilohertz. So beta equals WC2 minus WC1, the difference of the two corner frequencies. Now he converts the bandwidth to radians again to calculate R. So when you're solving for R or when you're solving for L, the rule then is to convert to radians if it's not already in radians. Okay. So how does he find resistance? He does R equals beta times L, because beta is R by L, and so with that he comes up with about 143 for R. So we have R, L, and C, and we have the center frequency. The corner frequencies were given. I guess that's really all there is to it. He does do a double check by substituting these values back in equations 1414 and 1415, which are the ones I had given you on, I think, the previous slide, on slide 27, no, 26. So you see for RLC series circuit, that formula for omega C1 and omega C2. Now we already know omega C1 and C2, right? Because those are, hold on, I gotta pause this. Okay, he uses these formulas for omega C1 and omega C2 that were on slide 26 just as a double check on whether if you use these RC values and use those formulas, you get back the original 1000 hertz to 10,000 hertz as the corner frequency, as the band, which he does get. Okay, so that is the example. It was, I think, a pretty simple one. There's a few other things he mentions. Please read the whole thing. I think it's important because there's a lot of nice points, nice tips and hints that he gives you on how to solve these kind of problems. One thing I wanted to say is he says it's almost always easiest to calculate the center frequency and the bandwidth first, and from there other things like corner frequencies can then be calculated. Okay. All right, so I'm going to move to 14.7, which is the same problem, same basic circuit RLC, but now we have this additional RI that he introduces. And to make things simple, I guess he says use RL or Ri to be the same value as R, which was in the previous circuit. Now remember, in the previous circuit he solves for R and comes up with 143 as the value. So we can use the same value. So here actually the first part of the problem, he actually helps to determine the transfer function. And this is where I copied it from, and I already gave it to you in somewhere. I think if you go back to band pass filters, let's see, with the series resistor. Oh, maybe I didn't give it to you. Okay, so but the formulas are here. He does show you on page 558. The omega 0 formula is still the same. So the center frequency, nothing changes. The corner frequencies, instead of R, simple, we just bring in R plus Ri. And that's the only change that he makes in those formulas for omega C1, omega C2, that is the two corner frequencies. Also bandwidth, same thing, instead of R by L, he just does R plus Ri by L. And similarly Q, which is omega O by beta, also just has R plus Ri. So everywhere where there is R, you add, you make it R plus Ri. So that's the derivation, and it is in the chapter, so please take a look. It is in the example and become familiar. So in part B, he actually uses this derivation to solve for the numerical values. So what changes happen? So once you substitute R plus Ri everywhere for just R, then I mean the bandwidth is still given, so we can't really change that. The center frequency also is given, that's part of the problem, so we have to, that stays the same. What changes? So bandwidth becomes R plus Ri by L. So previously it was just R by L, the bandwidth was 9 kilohertz. Now it becomes 18 kilohertz, which actually makes for very poor performance, right? You wanted to design a graphic equalizer for 1000 to 10,000 hertz, but now your equalizer is doing the same, it's giving the same treatment all the way to 18 kilohertz. That's no good, is it? Isn't it? So the beta, the bandwidth has become double, and to make things worse, the maximum gain has become half. So originally the maximum gain was 1, right? This is what you always want from an amplifier, from a filter. But with the new resistance, it drops to half. So that is the problem with having additional resistances. We saw that when we had a load resistance in some filters. Now we have a series source resistance, and we others have the same problem. So to summarize, he does that actually at the bottom of this page. He says, adding a non-zero source resistance to a series RLC bandpass filter leaves the center frequency unchanged but widens the passband. That means it allows more frequencies to go through and also reduces the passband magnitude. It dropped it from 1 to 0.5 in this case. Okay, so that was the example. Two examples related to a series RLC circuit. Let's now take a look at 14.6. Example 14.6. This is on page also 555 in my textbook, and this is to design a parallel RLC bandpass filter. So again, he actually derives the equations for the center frequency, the bandwidth, the corner frequency, the quality factor. He does the derivation for all this, and for this is where I copied everything from to paste it somewhere else so that we can proceed with solving problems. But again, take a look, see how he handles this, and it will be beneficial for you. Let's just try and finish part D. D is where he says, okay, assume a value of 5 microfarads for the C. So there is a C here, as you can tell, in the circuit. So that we start with an assumption, and create a bandpass filter with a center frequency of 5 kilohertz and a bandwidth of 200 hertz. So he's giving us everything in hertz again, and so which we can use. Maybe we have to convert to radians also at some point, but all the data is there. Okay, so let's see what exactly he does to solve it. First thing he does is to find R using the formula beta equals 1 by RC, so that R becomes 1 by beta C, and beta has been given a bandwidth of 200 hertz. So that 200 hertz definitely he has converted to radians. So that's important to do. You can see that on the page. And then C is just in microfarads, and he just puts that in, and he comes up with a resistance of about 159 ohms. Okay. Next thing he does is find the value of L. So you need all values, right? When they say design something, it means find the unknowns. So to find L, he uses the definition of omega 0, omega center, omega O. So omega O square is 1 by LC, and we know C, and we know omega 0 because that should be the center frequency 5 kilohertz. So again, convert the 5 kilohertz to radians and use the formula for L, and this time we come up with 202 microhenries or 0.2 millihenries. Okay. So we've designed the circuit. We've got R, L, and luckily he's not asking us to find anything else. Cutoff frequency. I mean, we can always find the cutoff frequencies. He has derived the formulas. They're available, and I've given them to you, but he has not asked for it. Okay, so let me finish that. We're going to skip to the next slide, and here I'm solving problems 1424 and 1425 from the back of the chapter. Okay, and both these problems have to do with the same bandpass filter, and they do have a 20 ohm series resistance or source resistance, as you can see. So nothing new here, at least not in the first part. But the second part may be a little more interesting because we have to do some, we have given a input voltage as a cost function, 0.5 cos omega t, and we have to find an output function. Okay, so let's solve this problem together. And again, also remember, he wants us to find the values in Fs, in hertz, not radians, at least some of these frequencies, which is a bit unusual, but you know, that's, he's the boss, so we have to make sure we answer him correctly. Okay, so I'm going to open up my PDF and let's look at 1424 and 1425. So 1424 and 1425. Okay, so 1424 is on the top of page 5 of my handwritten PDF. So hopefully everybody can go there. So the nice thing is all the values in the circuit are known. RLC, even the RI. We just have to use the formulas and start plugging in these values, and we should get the answers that he wants. Okay, so omega 0 is 1 by LC, omega 0 square, and so we get omega 0, as you can see, 625 times 10 power 6. Omega 0 is the square root of omega 0 square, and that's 25 times 10 power 3. To find F0, which is what he wants in hertz, you have to do the division, omega 0 divided by 2 pi. Okay. I just calculated K here quickly. I think we have to use it somewhere else. But K, remember, is R by R plus Ri. So in this case, it's 180 by 180 plus 20, which is 180 by 200 or 0.9. Okay. All right. So F0 is known, omega is known. What's the next step? We need Q. Q is root L by C divided by R plus Ri. If there is no Ri, if there was no source resistance, it would just be root L by C by R. But we have the R plus Ri because of the source resistance. And if you solve for that, you get a nice value of 5, as I show here. So Q is 5. Q is a quality factor. Using this and the other formulas that previously we have already seen, we now need to find the corner frequencies. So first I calculate omega C1, the lower corner frequency. It comes out to be this value. Then I convert that to hertz, and that's 3.6 hertz. Same method to find omega C2, the second corner frequency, and that comes out to be 4.4 kilohertz. So the bandwidth is, you can write, I think, the bandwidth either in kiloradians or in hertz. Either way, I think, is okay. So anyway, you see the values there, 5 k radians or 766 hertz. Okay, so the only thing new and important is to remember that when there is a series resistance, Ri, a source resistance, always carry that R plus Ri into the formulas, because otherwise we don't need that R plus Ri, but with the presence of that resistance, some of the formulas change. Okay. All right. Next problem is a continuation of the same problem. So everything we derived up there for 1424, and now I've scrolled down to page 6 of my PDF. Now we have been given an input as a cost function, 0.5 cos omega t, right? And so using this information, he wants us to find the expression for the output voltage. Remember, the output voltage is the voltage across one of the resistors, right, the R. That's how we define a band pass filter. So he is asking us to use all the information we have and the fact that there is an input signal. It's a simple cos function, 0.5 cos omega t, and give all the output values at 2 or 3 different frequencies. Okay, so what do we need to do? We've got the input, the voltage input. The first thing to do, of course, is to create the transfer function. And there is a simple formula for the transfer function which also he derived when he did the derivation as part of example 14.7. So everything here comes from example 14.7, and in solving ABC of 14.7, he actually gives that formula that I've written here. You can see that is on the top of page 558 of the textbook under example 14.7. So take a look and you will find that example, find that formula. Okay, so we have the formula, we know beta, we know K, we plug all that in and we come up with an expression in S, and we also know omega 0, right? That was given to be 2500, right? So we've got 25,000 radians per second was given to be the no, we calculated that, right? Yeah, based on all these values, RLC values, one of the first things we did was to calculate the center frequency as 25,000 radians per second. So we've got that, we've got that 25,000 here, we've got beta as 5,000, we got K as 0.9, and so we plug all that in and we come up with this nice expression for the transfer function as a function in S as 4500 S by S squared plus 5000 S plus a constant. So whenever you're asked to do frequency response, I think we've already done a couple of problems, so this shouldn't be new to you. We just substitute j omega for S, and so you have an expression in j omega. Omega, you now start to use different values, right? And generally the way they seem to give it here is they'll give you, okay, find the output when omega is the center frequency, omega 0. Or they may say find it at the corner frequencies, omega C1, C2. Or they may say find it 2 times omega 0, right? We've seen all these problems or questions. So basically what you do is you substitute for omega a specific value, right? In this case, the first thing we have done is we have taken that omega 0, which is 25k radians, plug that in. You know, when you're looking at the center frequency, you should get an output value pretty close to 1, right? If there was no series resistance, it would be 1, but we do have a series resistance, so it actually dropped slightly to 0.9, but that is the magnitude, and 0 degrees. The phase shift is always 0 at the center frequency because it's a resonant frequency, remember. So you're not surprised that it comes out to be 0 phase shift. So that's how you write the output expression. You remember, output equals transfer function times input, right? HS times input. So that's how I've written this formula, this equation. Similarly, we have to do 2 more, and one at the corner frequency 1, the other at the corner frequency 2. I show you the derivation. Part of it was gone, so I rewrote it, but you can see how the correct way of writing the expression for the output frequency is. Okay, the magnitude and the phase angle changes, the frequency for which you are assessing this output, that obviously stays the same. That's the input frequency, that comes out as the output frequency. Okay, so we are already 30 minutes into this, and so I've got lots of things open, but where is my PowerPoint? Here it is. Okay. Um, let's move on. I think we finished with band stop or band pass. So the next thing we are going to look at here is band reject or band stop. We've got a few problems here also to solve. All of this theory we already covered, so I'm not going to repeat it. You know that, hopefully you know by now, that in a band stop in a series RLC circuit, if you take the output across the combination of the inductance and the capacitance, that makes it a band reject filter or a band stop. And then there's also a parallel way to make the band stop. Okay, so I will move ahead to example 14.8. And that is the first example on band rejects, and it is on page, okay, let's see, page 562 of my textbook. And let's see what he wants us to do. So this is a simple series RLC circuit, sorry, and the output, as you can see, is across L and C, and he has given us some requirements. He's given us a bandwidth 250 Hertz, center frequency has to be 750, and he says use a 100 nanofarad capacitor. So lots of things have already been given, compute RL and the corner frequencies and Q. So pretty straightforward. All he does is quickly plug in values. He first begins by finding Q, which comes out to be 3. Then he does the calculation for L, which comes out to be 450 millihenries. Then he uses the definition of beta as R by L to come up with R as 707. Then he calculates omega 1, omega C1 and omega C2. The formulas he uses are interesting. Please make a note of it. Instead of using the formulas for corner frequency that we've generally used, which is to put in the values of the R and the L or the R and the LC, he is just using betas. So the corner frequencies looks like there's like 3 different ways to calculate. You can either go with using the values of the resistance, inductance, capacitance, or you can find the bandwidth and use the bandwidth values along with the center frequency, or you can find the Q and use the value of Q along with the center frequency. So these are 3 different methods. Please become familiar. I haven't shown all of them in my PowerPoint, but they are in the textbook in a couple of places. So please make a note and do appreciate the fact that he has used the beta formula, meaning he's using the bandwidth to come up with the corner frequencies. Okay, so he comes up with 3992 radians per second and 5562 radians per second as the 2 corner frequencies, and then he converts them to hertz, and then he takes the difference to show it to be 250, which is what we wanted. And the geometric mean also he calculates again to show that that's the center frequency of 750 Hertz. Okay, so that was a quick look at 14.8. I do have a couple more problems from the back that I have solved. So maybe we can do that together, and that will benefit you. It will give you some more practice. And then really we are done with the chapter. This is the last set of problems and we are done. I do have some more quick material on active filters. So you can sit back and listen to that when I get to that. If you're interested, you can follow. If you're not, you don't have to, because it certainly won't appear in any exams. My exams, I'm sure in the future you may have some exams that have that. But yeah, so let's quickly get through these two problems, 1442 and 1443. So what is 1442? And 1443, as you may guess, is just a continuation of 42. So 42, he has given us a band reject filter, not in a series version like I just showed you the previous example, but this is a parallel version, and now the output is across R. The output voltage comes out across the resistance and not the inductance capacitance combination. So he gives us some data. He says the quality factor is Q of 5 and a center frequency F0, which is the in hertz of 4 kilohertz. So these are the items he's given us. Also, yeah, another thing he says is use a 500 nanofarad capacitor. So using all this information, find A, R and L, resistance and inductance, B, find the upper and lower corner frequencies in kilohertz, and C, calculate the filter bandwidth in kilohertz. So he wants everything in kilohertz. As you may understand by now, I think most of us are much more comfortable thinking in kilohertz. A lot of applications happen in kilohertz, but you can't avoid having to convert to radians because many of the formulas are in radians. So that's a big difference. So you have to keep going between the two. Okay, so that was problem 1442. Let's also see what we have for 1443, and then we'll go and solve them together. All that is happening is a load resistance in parallel, so 1K ohm resistance, has been now introduced in parallel to R. Okay, so this is not a series source resistance anymore, but we come back to having a parallel load resistance. And so what to do, how to handle that is what we need to address in 1443. And one thing I found as I was trying to solve the problem, and that's why I point it out here before we move away from this slide, which is, by the way, slide 37. For those of you who have been patiently waiting for me to tell you that slide number, it's 37. The two formulas we are using to find two things about them. Firstly, they are in the Q form. Okay. Secondly, what I discovered is you can actually directly use the F version, meaning directly get the answer in hertz, rather than have to first do omega in radians and then come to hertz. So apparently some of these formulas, they work directly. Definitely the formulas for that use the beta, the bandwidth, and the formula that uses the Q, the quality factor, both of these, if you need it, you can directly calculate in hertz. You don't have to first do it in radians. Okay? All right. So now let's see how to solve this problem, these two problems. So I'm going to minimize this and go to the top of page 7, which is my of my notes, my PDF notes for these two problems. Okay, so you can see my nice little picture there. Of course, in the first part, 1442, there's no RL, so ignore that for the moment. Q is 5, C is known, F0, center frequency 4 kilohertz. So omega 0, I find it as 2 pi f, which is 8 pi kiloradians per second. Now you can see how L and C are derived. Use the formulas. Remember, when you're doing these calculations, L and R, you have to have the frequency in radians. Otherwise, you'll make a mistake. Okay. So L comes out to be some millihenries, R is close to 400 ohms. Part B, find the corner frequencies. Here I'm sticking with the RC methodology. So, well, it's RL, I apologize, yeah. RL, yep, I think that's RL. Yeah, it's R by, hold on, let me confirm, I don't want to give you the bad information. Okay, we'll have to look at this just to double check. For a parallel RLC circuit, the formulas have RC in the denominator. Okay, we checked on slide 34 for those of you who are looking or just listening. So the formulas are shown and the denominators are RC, and so I'm happy we checked. So we can go back to my PDF, and everything on the denominator is a C. And so what I do, just to make this calculation easy, I just find that 1 by 2 RC separately, and then 1 by LC also I find it separately and put that aside, and then I substitute that to find the corner frequencies omega C1, omega C2, 22712 and 27738, which convert to 3614 Hertz and 4414 Hertz. Okay. Then the betas, the beta is the bandwidth, which is just the difference. First I find it in radians and then I convert to Hertz. Okay. Now the 1K resistor is added, right? Here it is. So there is no real guidance in the textbook. He has not told us what to do with something like that. So here's my method, and I hope that's right. So what I did is I just combined the two resistances. They are in parallel, so you can always say, okay, equivalent resistance. Once you have that equivalent resistance, pretty much all the other formulas apply. So that's the method I used. So here it is. First I do the parallel of the two, and that comes out to 284. Then I use the formula for, actually I write the Q as omega 0 RC. That is a formula that's somewhere in the textbook, and that comes out to be 3.58. So Q went from being a higher value. I think we were given Q5, and now we find that Q has dropped to 3.58. So the quality in some sense has reduced. Beta is F0 by Q. The center frequency always stays the same. So that is still 4000, and we reduce that, the Q reduced, so beta is higher. So the bandwidth has stretched. Now to find FC1, the corner frequency, directly in Hertz, I use the formula I just showed you, both for FC2 and FC1, and so we get these two values. Okay? So I hope this was simple enough. I think with this we pretty much finish all of the filters business, the 4 different types of filters in chapter 14, meaning passive filters, right? So I hope you have a good sense of all the concepts and the ideas and the number of formulas. Try to become familiar with as many of them as possible. And learn at least one good method or one good formula in each case, if not all of them. I mean, ideally you are able to recollect all of the others, but if not, at least have one good method, and then you can always use that method consistently to solve the problems. Or if you are able to remember the beta form, the Q form of the formulas also, that's good also. Okay. All right, so we have another 5 minutes. I'm going to go back. Let's see, what else do I have? Yeah, that's the end of my PDF. I'm going to go back to my PowerPoint, and let's just briefly, quickly look at a couple of examples on active filters also. just so you feel some sense that, okay, you understood, you at least know a little of, that I taught you a little of active filters also. So I showed you these drawings, these circuit diagrams. The first order low pass filter, you see something called K, which is not the same K as the other cases. This K is strictly gain. It's R2 by R1, which is the ideal gain on an op-amp circuit, or RF by Ri actually, with a negative sign. And then here the corner frequency for a simple low pass filter is just 1 by RC, well, R2C, meaning the feedback R, okay. And then the transfer function compared to a regular RC or RL first order circuit, it has this additional factor K that appears, okay. And I showed you these formulas. I think we quickly went through this low pass, high pass, band stop, etc. So all that I've skipped, but I have gone on to example 15.1. I think that's really, I've got one example from the textbook and one problem that I found somewhere else, and that's it. That's the end of the chapter. So let's look at the example 15.1. This is, I thought this was too simple an exercise. He does, it's a good example. It would be good to read it and understand it. But the point I find a little funny is that everything comes out to have a value of 1, and so that makes it a little hard to see the benefit of it. Anyway, let's quickly walk through it. So there's a circuit, there's an op-amp circuit, and what he gives us is that the op-amp achieve a low pass filter with a gain of 1. So still we haven't gone away from 1, right? Also a cutoff frequency, also a 1 radian per second. And lastly, he says use the R1 resistor, the input resistor, as 1. So lots of 1s here, but nevertheless, that's how he gave the example. And the one interesting thing, I'll come to that in a second, but so use this method, and he shows it in the textbook so you can follow along. But we do end up with values again of R2 also 1, C also 1, so everything is 1. He didn't ask for this, but I did write this. The transfer function can be written like this using the formula. So it becomes minus 1 by 1 plus S, or S plus 1. You can put the j omega in to convert it to the frequency domain and come up with the frequency domain transfer function, and that's minus 1 plus j omega. Now, if you punch a value of omega equals 1, right, which is the corner frequency, cutoff frequency. So at the cutoff frequency of omega equals 1, this whole transfer function comes out. In your calculator, you can put it in and it will come out in a neat polar form. I think the angle comes out to be 130 or something, and the magnitude comes out to be 1 by root 2. And I wanted to make the point, which wasn't very clearly made in the textbook, but you can see he did give us the board plot. So I'm happy that we are back to understanding the importance of board plot, because we didn't see much of that in the previous chapter, the passive filters, but here it's here. And so I thought I must calculate at the cutoff frequency the magnitude of the response in decibels and show you that it is minus 3 dB, right? Because we call this the 3 dB point, or the half power point. So if you do the calculation and you do the calculation of the magnitude of the output, you come up with this minus 3 dB. Remember, this is a unity gain. That's a gain of 1 filter. If it was a gain of 4 or 5, then this won't apply. But as long as it's a unity gain, 1 gain, then this 3 dB point must appear, and it does. So I marked that point. Okay. All right. So I hope that was beneficial. I have just one more last slide. Give me 2 more minutes and we'll be done. I picked this problem somewhere else. It has a little more of a more realistic question, which is design a low pass active filter with a DC gain of 4, -4, not just 1. And the corner frequency is not just 1 hertz or 1 radians, it's actually 500 hertz. So if you are given a problem like this, how do you solve it? Quickly, omega, first find omega as 2 pi f, and that is also 1 by 2f RC. The next step is to find, to use the value, the fact that the gain is -4, so minus RF by RC equals -4. He's got two formulas, but they still can't be solved because there's 3 unknowns, so you have to still make an assumption on one. So he says, okay, let's pick CF equals 0.2 micro, and then he solves for RF, he solves for RI, and so how do you actually build the circuit? Because there's no 1.59 in the lab, there's no 397 in the lab, so he says pick the nearest value, so pick 1.6K, and Ri equals 400 ohms, and hey, you can build the circuit. Okay, so I hope that was also useful. Again, active filters, I'm not going to test you in the exam and all that, but this is just for you to feel that you've been introduced to the idea. But I hope the rest of the material you did reasonably understand. Try to solve the homework problems, look at the class problems again, look at the examples, read the textbook, read the PowerPoint, and you should be good. Write to me if you have any questions. Okay? Thank you.